Thank you for coming to our review session. I'd like to first of all announce that in addition to my regular office hours, which are 10 to 10:50 Monday, Wednesday, and Friday, and noon to 1 p.m. on Friday, because of my schedule this week, I can have additional office hours tomorrow from 9 a.m. to noon, in case you have any additional questions. Okay, I can't do that every Tuesday, but this Tuesday it works out. Okay. So you all have the packet. This is the packet. Okay, with the instructions that I've mentioned at the top. Okay, so you can see the instructions. Has everybody been able to download this? Okay. So the rest of the review session will be, I'll just go through problems that you're having issues with. 11. So a sealed piston apparatus contains air, frictionless piston, holds a constant pressure. We're given the pressure, heat is added, causing the air in the cylinder to expand. So this is a constant pressure system. We want to calculate the work performed in going from state 1 to state 2. So for a constant pressure system, the work from 1 to 2, which is normally an integral of PdV, becomes P times the final volume minus the initial volume. So the first step, we're given the dimensions of the cylinder, right? Okay. So the cylinder has a diameter of 12 inches. What we need to do is get the initial and final volumes, because we're given the pressure, right? We're given the pressure is equal to 20 pounds force per inch squared. So what are our volumes? We're going from an initial volume of 6 inches up to a final volume of 10 inches. We're given the pressure, 20 pounds force per inch squared. What we need are the volumes. Do you have enough information to get the volumes? Yeah. So how would we do that? The volume is going to be the area times some height. So the area is going to be pi over 4 times 12 inches squared, which is going to be what? Somebody have that? This is a group exercise, so you all have to help me out here because I'm not running the numbers here. You are.
113.1.
Okay. So this is 113.1 inches squared. So what's my initial volume? It's going to be 113.1 inches squared times 6 inches. And my final volume is going to be 113.1 inches squared times 10 inches. So this is going to be 1131 inches cubed. What's our initial volume?
678.5.
678.5 inches cubed. Okay, so we could do this problem and let's we could do this one of two different ways. We can convert this to feet cubed and convert this to pounds force per foot squared. But let's just do it in inches. And if we're consistent with the units, it'll all work out. We now have all the numbers we need to plug in here. So the work from 1 to 2 is going to be 20 pounds force per inch squared times my final volume, which is 1131 inches cubed minus 678.5 inches cubed. So what does this come out to be? $9,050. And what are my units? Is that right? This is going to be what? Inches, pounds. Okay. How would I convert to foot pounds? Yeah. Yeah, divide by 12. Looks like we may have a problem with the answer here. Foot over 12 inches, which gives me what? Sorry? 754 foot-pounds force. All right. So this one has 3,017. So what's the problem here? This looks right.
Where did the 4 come from?
Oh, you know what? We don't do that because this is pi d squared. Will that change things? You betcha. All right. Well, you know what? If something's worth doing, it's worth doing over. Here we go.
Why would you give it the over 4? You're using just diameter, not radius.
Because I'm using diameter, not radius.
Yeah, then you put it over 4 if you're using diameter.
Oh, no, we would. Yeah, that's right. Pi over 4d squared.
If you're using radius, you don't.
That's right. And so then it was 113.1. Okay. So based on what I'm hearing from you folks, this is 754 foot-pounds. Okay. If the internal energy increases by 9.67 BTUs, determine the heat transfer during this process. So is this work into the system or out of the system? Well, is this an expansion? Right, this came out positive, so that means it's work out of the system. Okay, so if we draw a first law, I've got.
You get rid of over 4, you get units above.
If you do the what?
If you take give out the over 4.
If you get rid of that?
You get
Oh, okay, so that's. Oh, that's the issue. Okay, so we're just off by a factor of 4 here. That's the issue. So, okay. Well, we'll proceed the way we'll proceed with these numbers here.
Which one would be right?
This is the right one. Okay. So then this one I'll just write it up here. What would it be? This is going to be 754 foot-pounds. Now, the internal energy is increasing. We know the workout, delta U, which is U2 minus U1, is increasing by what? 9.67 BTUs. So I want to figure out what is the heat transfer. Well, the first law is that Q in minus the work out is equal to U2 minus U1, right? Okay. Now, this is given in BTUs. Okay. So if I add the work to that, then I should be able to get the heat transfer. But what do I have to do with the work?
Convert it to BTUs.
Convert it to BTUs. So the 754, the way we convert that to BTUs is to say that a BTU over 778 foot-pounds. And what does this come out to be? 754 divided by 778.
0.969.
Okay, so the work here is then 0.969 BTUs. And so if I plug into this equation here, I have Q minus 0.969 BTUs is equal to 9.67 BTUs. Q comes out to be what? 10.6 BTUs. And this comes out to be positive. So this is 10.6. And that's positive is the heat into or out of the system. If the heat is positive, is that heat in or is that heat out? That's going to be what? That's going to be heat in. So I'm adding heat So I've got heat coming into the system, which is 10.6 BTUs. My internal energy is going up 9.7, and then work is coming out. Okay, so that's the way you write this first law. Okay, the heat and again, if heat in, if it's positive, it's heat in. If it's work out, it's positive, is equal to the final state minus the initial state. And here, I basically have to give you the internal energy because we don't know how to calculate it yet. But in a week or so, we'll learn how to calculate the internal energy of air. Okay. Any questions on this one?
If heat's going in, work's always going up, right? There's not such thing, heat in, working.
Could be. Yeah, it could be. Heat coming in, and there could be work coming in, but then the work would appear in here as negative, and then there'd be a lot more change in internal energy. Yes. Yes?
A question about number 5 is a pressure problem. And so P equals rho H, right?
Let's take a look. Number 5?
Yeah.
Okay.
I think the answer you had on the paper pressure of the air. I thought it was supposed to be rho GH plus the pressure of the air to get absolute pressure.
Well, let's see. The density, the numeric value is going to be right. What the density does here, because it's water, is it's giving us basically a factor of 1,000. Okay, so let's go through this. So spacecraft, let's see, which, is it this one, number 5? Okay. So we've got pressure is equal to rho times G times H. So this is going to be 1,000 kilograms per meter cubed times G, which is what? 1.62 meters per second squared. And then what's H? H is 1.5 meters. Okay. So what does this come out to be? This is 2,000. What is it now?
2430.
2430. And what are the units on this?
Kilogram meter per second squared.
That's a, well, let's see. It is a,
Sorry, kilogram per meter second squared.
yeah, this here is going to give us a Newton, and this is going to be a Newton per meter squared. So this is 2.43 kilopascals. Okay, and then we add to that 90. And we get about 92.4 kilopascals, because this is the air pressure, right? Yeah. But if you work this through, you would get, if you left the density off, you would get what? You would get 2.43, except it would be pascals. And if you look ahead, you think, oh, I get that just by just without the density. But the density is what enables you to add the kilopascals and the kilopascals. So you are adding 2.43 pascals to 90 kilopascals.
Okay.
You see that?
Yep.
That happy coincidence wouldn't have happened if we were in English units. It's just that the density basically gives us that factor of 1,000.
Okay.
Any other questions on this one? Another important takeaway of this is that the density doesn't change if we're on a different planet or if there's another gravity. The density is the density because the mass is the mass. Mm-hmm. Yes?
How does this one differ from 6A?
6A. Let's take a look. How does this one differ from 6A? It is pretty much identical, except we have to be careful because the density of our fuel is given in pounds. And so we have to remember that the definition of a pound is based on the Earth's gravitational acceleration. So the best way to approach this problem is to convert the pounds to slugs. And if you convert the pounds to slugs, you can basically solve the problem the same way. Okay? So the density here is what? It is 51.2 pounds per foot cubed, but if I multiply by our conversion factor, slugs over 32.2 pounds, what do I get? It's what? 1.59 slugs per foot cubed. Okay? You'll notice that this conversion factor stays the same even though we're on Mars, because this is a mass conversion factor. Okay? And that doesn't change. Once we're in slugs, we multiply this, so my pressure here is equal to rho, which is 1.59 slugs per foot cubed, times our local gravity on Mars, which is 12.2 feet per second squared. And then we multiply that by the depth of the tank, which is 3 feet. And what does this pressure come out to be? What's the number? 1.59 times 12.2 times 3.
58.2.
58.2. Okay, so now let's work on what the units are. We've got a slug foot per second squared. One slug accelerated at 1 foot per second squared is a pound force. We've got pounds force times feet divided by feet cubed. This is pounds force per foot squared. Okay. We're given the temperature at the top of the tank in terms of inches squared. So if you wanted to add those two, you'd have to reconcile that difference. So the absolute pressure, this is my gauge pressure. This is going to be 58.2 pounds force per foot squared. Times what? If I want to convert it to PSIA, this is then feet over 12 inches squared plus what? 3 pounds force per inches squared. And that would be the absolute pressure. So to get back to your question, the difference between this one and the previous one is in the metric system, we were given our density in terms of basic mass units, whereas here we were not. We were given it in terms of pounds, and to then multiply by a local acceleration, we had to convert it to slugs. Any other questions on this one?
Can you go over how to do part D of this question?
Part D. Part B. What is the specific gravity of this fuel? Oh. Specific gravity is equal to the density of the liquid over the density of water. So for this problem, that is going to be what? Let's go back up here. our density was 51.2 pounds per foot cubed divided by the density of water. The density of water is 62.43 pounds per foot cubed. And you can just take that ratio. Okay. You'll notice that I don't have to convert to slugs here because the specific gravity is unitless. Okay, so if I'm in consistent units, I could have converted both of these to slugs. It would have been dividing both of them by 32.2. We didn't need to do that. It comes out unitless. Does everybody know the difference between this and the specific weight? What is the specific weight? This is this Greek letter gamma, and this is equal to rho g. Now, in this case, we have to be in slugs. And so let's figure out what the specific weight is for our fuel here. This is not in this particular problem, but we might as well do it while we're here. So we go back, we're going to use the density in slugs, 1.59 slugs per foot cubed. And we're going to multiply this by 12.2 feet per second squared. So what is this? What's the number, first of all? Let's get the number. This is going to be 19.4. And now what are my units? Yes?
It always has to be in slugs or just for this problem?
If you want to just use rho g, it has to be in slugs. Now you could use rho g over gc. Remember that constant?
Oh yeah, that was for...
Okay. We could use rho g over gc, and then this could be in pounds. But then you'd have to use gc, which is basically 32.2 pounds force second squared, which is essentially the same factor inverted. Okay, so yes, you can avoid the word slug by doing this, or you can just realize, what are our units here? I've got what? I've got 1 pound force is equal to a slug foot per second squared. So this is 19.4 pounds force per foot cubed. Now, why would I want to do that? Well, if you're looking at hydrostatic pressure, the pressure can also be written gamma h. So once I have that, I just multiply this by 3 feet, and I've got the pressure. Any other questions on this one? All right. Any other problems you want to look at? Can I, pardon me?
We go over 7.
7. Ah, there's a good one. The manometer shown below is used to measure pressure in an oil tank. Okay, and so, let's see. So determine the specific weight of the oil. How do we get the specific weight? Yeah. The specific weight of the oil is going to be what? It's going to be the density of the oil times G. So this is going to be 800 kilograms per meter cubed times G, which here we're given 9.807 meters per second squared. And if you're given a value of G, use that value of G, because the specific weight is not like the density. The density doesn't depend on weight. The specific weight does depend on the gravitational acceleration. Okay? And so this would be what?
7,845.
7845. And my units are what? Kilogram meter per second squared. Remember, 1 Newton is 1 kilogram meter per second squared. So this is 7845 newtons per meter cubed. That's the specific weight of the oil. Or here it's 7848, depending on how you round things.
Is there a certain unit for density in the English system that we're supposed to use? Or is it scientific system? Yeah.
The SI system? Density will be in kilograms per meter cubed. Okay, that's easy because there's only one unit of mass in the SI system. In the English system, you've got pounds, you've got slugs. Problems like this, just to convert to slugs. That's the easiest thing you can do. So determine the specific weight of the oil. Determine the gauge pressures P1 and P2 in pascals. Once I've got the specific weight, P1 is going to be gamma times Z1. P2 is gamma Z2. Okay? So that's 78, we'll use this, 7848 newtons per meter cubed, and Z1 is going to be, that's in centimeters, right? So I'm going to convert that to meters. And then we've got 7848 newtons per meter cubed times Z2, where Z2 is 0.3 meters. Everybody see that? All right. So, calculate the specific gravity of the glycerin. So what do we know about the glycerin? We know its specific weight. Could I just use the specific weight here instead? Okay, if I multiplied this by G over G, what would I have? This would be the specific weight of the fluid over the specific weight of water. Everybody see that? And as long as I'm measuring them both in the same gravitational area, this will work. Everybody see that? Okay. So then, what's the specific weight of water?
9,800.
Yeah, well, we've got to get the specific weight of water. We don't have that yet. this is going to be what? This is going to be gamma of water is going to be 1,000 kilograms per meter cubed times what? 9.807 meters per second squared. So this is 9807 newtons per meter cubed. And then the specific weight of the glycerin was what? 12,370? Yeah, and then you just take that ratio. And that should be unitless. Everybody see that?
Oh, never mind.
Question.
No, never mind.
In this case, glycerin is denser than water, so it's greater than 1. You see that? All right. Calculate the manometer fluid column height. So now let's look at this. This is our fluid column height. Here you see that P2. Where does P2 come across into that manometer? Here's my tank. Okay. And here's P2. Is this fluid the same as this fluid? Yeah. So then if I come across here, these are all lines of constant pressure. The pressure here is the same as the pressure here. The pressure here is the same as the pressure here. So in this manometer, this is P2. Okay. Well, here's my glycerin. So this is another liquid down here. And I've got lines of equal pressure through this glycerin also. For instance, the pressure here is the same as the pressure there, which is P2 that we calculated in the previous section. Okay, so this is P2. Okay. This P2 is at the bottom of a fluid column of some height delta H. So P2 is going to be the specific weight of the glycerin times delta H, which is the same as the P2 value was here. So what was P2 here? This value here. It was what? 2354 pascals. And it's the same thing here. 2354 pascals, which is 2354 newtons per meter cubed. So if I take this value and I divide by the specific weight of the glycerin, I should get delta H. Okay. Everybody see that? Any other questions? Okay, so we've let's see, we've done some force and mass, weight, hydrostatic pressure, manometer. We did a constant pressure process. We did the first law. Yes?
With what you just went over, wouldn't that cancel out your units? 'Cause if you're dividing by a Newton per meter cube,
Oops, no, this is a Pascal is what? A Pascal is a Newton per meter squared. Yeah, this is pressure. So if I want to solve for delta H, this is going to be what? This is going to be 2354 newtons per meter squared. I'm going to divide by the specific weight of the glycerin, which is 12,370 newtons per meter cubed. You can see that what I'm left with is units of meters. Yep, good. Thanks for catching that. Yes?
I know you will consider atmosphere pressure in this problem, but we have atmosphere pressure on the glycerin.
Well, in this problem, we've got air pressure up here, and we've got air pressure here. So it cancels out. You would have to, you can assume that. I would have had to tell you if there was different pressure up here. Yeah, that's a good question. Yeah, if something looks like this, it's open to the atmosphere. Yep. Yes?
On 8B, says, well, the radio control all air plant less than 2 kilograms. Flies at a constant velocity of 30 meters per second, which is 1/2 mv squared.
And the answer is 900 joules.
So, okay, no, I see what I did wrong.
Yeah, kinetic energy is going to be 1/2 times 2 kilograms times 30 meters per second squared. And so this is going to be 1/2 times 2 kilograms times 900 meters squared per second squared. So the 2's cancel out, and we're left with 900 kilogram meters squared per second squared, and this is a joule.
Okay, yeah.
Yep. Yep. We have the same issue here. How would this problem be different if it was in English units? Convert to slugs. Yep. And then you'll have a slug foot squared per second squared, which is a pound force times a foot. Yep. Any other questions? Yes?
On 10C, is that just the first one?
Let's take a look. Yeah, this is almost like the one we did, except maybe the answers are right. But here, actually, this one here is more helpful because I actually say, calculate the initial and final volume. And then you take the difference and you get the joules. And you're right, this is just the first law. Because what I did is I gave you that the energy decreases by 800 joules. This is work into the system. And so let's draw a picture of what this looks like. This is problem 10C. Here's our apparatus. Now, in this case, this is a compression process. So I've got 356 joules of work in. My change in internal energy, which is U2 minus U1, is going to be a negative 888 joules. And we want to figure out what the work is. So heat minus the work is equal to delta U. So let's pull the work to the other side. Q is equal to delta U plus the work. This is equal to minus 888 joules minus 356 joules. Okay. That minus, when I bring the work to the other side, that becomes positive. And then I stick the negative value for work in here, okay, because this is work into the system. And then this comes out to be a minus 1245 joules. So what that means is I've got work coming in, and if this is negative, what's happening to the heat? Is it coming in or is it leaving? The heat is leaving. Everybody see that? So this is that's the first law, okay? And in this case, this is a compression process, so it's work being done to the system. So it's work coming into the system. And that comes in negative. Yeah. Any other questions? All right. Well, thank you for your attention.